Today's lesson is on gas law stoichiometry. So we're going to revisit stoichiometry, but now keeping in mind the actual gas laws that we've learned at the beginning of this gases and atmospheric chemistry unit. So let's recall. Stoichiometry refers to the relationship between the number of moles of the reactants and the number of moles of the products in a chemical reaction. So it's going to be really important that you know how to, remind yourself how to balance and how to put together formulas for this chapter of the unit. Now, according to Gay-Lussac's law of combining volumes, when gases react, the volumes of the reactants and the products measured at equal temperatures and pressures are always in whole number ratios. So what we looked at was how if we were, when we looked at the balanced equation and how the balanced equation represented like the coefficient in front of each compound when balancing also was equivalent to the number of liters that were found, right? So so the mole ratio is what we were trying to find with the stoichiometry before, but now we're looking at it in terms of actual volume. The mole ratios from a chemical equation are the same as the ratios of the volumes of gases. So if we had, let's say, X volume of a gas formed that was 1-to-1 ratio, the volume of the other gas would also be the same if they had the ratio 1-to-1 in terms of the number of moles. Okay, and we'll see that it'll make a little more sense when we actually go through some of the sample problems. So let's look at the first sample problem. Ammonia is produced by a reaction of nitrogen gas and hydrogen gas. Suppose that 12.0 liters of nitrogen gas reacts with hydrogen gas at the same temperature and pressure. A, what is the volume of the ammonia gas that is produced? B, what volume of hydrogen is actually being consumed? So before we actually try to figure out what kind of calculations we need to actually find here, first off, start off with your equation. And from this equation, we've also got the equation balanced. So from this information, what information do we have? Well, we have 12.0 liters of nitrogen gas. So we're trying to find the volume of ammonia gas and of the hydrogen gas. So these are the ones that we're trying to find. So now, going back to stoichiometry, right, and how we said, well, one thing I like to do is I like to list my unknowns first. So what we have here is, let's include one more. So we're trying to find hydrogen, ammonia, and we've got nitrogen. So these are the actual compounds that are involved with this equation. Before we were trying to find the number of moles and the number of molecules. And molecules in the sense of not the 6.02, we're treating it as the old-fashioned, the coefficient in front of each compound and the number of molecules that we're finding. But now we're going to add one more component to this. And in fact, one of them we're not actually going to use anymore. And it's this molecules one I'm going to ignore. So instead of it, what we're going to use is a mole to volume ratio. So let's look at the information that we have. Well, we've got a volume for nitrogen, which is 12.0 liters. We are trying to find the volume of the ammonia, and we're going to try to find the volume of the hydrogen. So I'm going to put volume there. I'm just going to write it because remember, we don't want to use the same letter for the unknowns. So, actually, you know what? Let's make things a little simpler. Let's keep that as X, and let's denote that as Y. So when we try to find it, we're trying to find this Y for our unknown. So let's look at the number of moles. So hydrogen, we've got we've got 3 moles. Right, we've got 3 moles of hydrogen. We've got 2 moles of ammonia gas, and we've got 1 mole of the nitrogen. So as we said before, what I like to do is separate the two sides. And what we're trying to do is, question asks us volume of the ammonia gas. So we're doing the ratio now of ammonia to nitrogen. Right? So the ammonia to nitrogen, we keep those numbers, so we've got 2 moles of the ammonia over 1 mole of the nitrogen gas. 2 moles is equivalent to however many, whatever the volume happens to be, over, what is the volume of the nitrogen? 12.0 liters. So all we're trying to do here is trying to isolate for our unknown volume of ammonia gas. So we're going to bring this 12.0 liters over, right? And we're going to have the volume of the ammonia gas is equal to 2 moles of the ammonia gas multiplied by 12.0 liters. We've got 1 mole of nitrogen here, right? And so what we're trying to do now is the units here cancel out. We multiply 2 times 12.0 and we get a volume for ammonia of 24.0 liters. Okay, and so pretty much you could almost figure this calculation out without having to actually go through the steps. So if we're going from 1 mole of nitrogen to 2 moles of ammonia, if the volume was 12 liters and we're going from 1 to 2, we're just multiplying by 2, which means the 12 we're multiplying by 2 to the original volume of the nitrogen to give us the volume of the ammonia, which means, now, to kind of save some time, right, let's ignore this one, right, because the next part of the question asks us for the volume of the hydrogen that's consumed. So we can go through these steps as we did with the ammonia, or we can look at what we've got. We're going from 1 mole of nitrogen to 3 moles of hydrogen, right, according to the ratio. So as a 1 to 3, so which means 12 liters is going to be multiplied by 1 to give us our volume. And 12.0 liters is going to be multiplied by 3 because it's a 1 to 3 ratio, which will give us a volume of 36.0 liters of hydrogen gas. Okay, so let's just kind of go back. So what did we find? The ammonia gas came out to 24.0 liters. The hydrogen came out to 36.0 liters. So we, even without having to go through all these calculations, we know that we're a 1 to 2 ratio for the ammonia. Right? So for this ammonia gas that we're producing, it's a 1 to 2 ratio. So it will be double the volume. All right? The hydrogen is 3 times the amount. Right? Hydrogen is 3 times the amount. Right? So whatever the volume is of the nitrogen, multiplied by 3, and in fact we're going to have 36.0 liters will be of hydrogen. Okay, so nice and simple.